All right, now we are going to be going through what Xanadu recently released, which is the Quantum Codebook. It's sort of like a textbook, interactive tutorial sort of thing, similar to the Qiskit textbook, but I imagine with more of a focus on quantum machine learning. I haven't looked at it at all yet. You can see this is the first screen if you were to open it up. And this is going to be something a little different than usual. I haven't prepared this. I haven't gone through this textbook at all. I want to see, what it's like. I always just show pre-written code, but I think there's some value in showing how to go about writing this code and how to go about solving problems. And so I think there's some value to doing this, raw or without sort of preparation. And so, I might have to look things up. I might have to refer to documentation, etc. I might have to think about it for a while. These are just sort of things that are always absent in my previous discussions, but I think have some value. And we'll see. If not, then I won't do this anymore. But I also just want to say that I had to agree to an end user license agreement to get to this page, I believe. Yeah, so if I do this, if I go back, maybe I already agreed to it. Yeah, there's like here it is. When I opened up the page, you have to agree to it as well. I didn't really read it because nobody ever reads these, but I just want to say if somehow some Xanadu person sees this, I don't know in here if it says you can't like use this for any sort of profit, but it's worth noting that I'm not monetizing this, that I'm gaining no profit from this. And if that's any sort of problem, I can always just take this down. But I just want to put it up there that this, if there is any sort of problems with this, that Xanadu can just let me know. So now we'll get into this. Looks like a nice little interface. All right, welcome to the codebook. I'm not going to read everything out loud. You can sort of follow along if you will. Exercise based. All right, I know how to program in Python and use NumPy. And, well, that's debatable. Sure, so there's different modules. Nice little graph over here you can see. These nodes will be in different colors. Okay, so basically there's tutorial, there's intro to PennyLane, algorithms, Grover's algorithm, and Hamiltonian. All right, so I think we'll just do the tutorial and probably the intro to quantum computing for now. Looks like there's a little, so there's going to be like the text over here, I guess, and the code over here. All right, so add two numbers. That is straightforward to do. We could simply add them. I don't know how it's judging this actually. I wonder, is it like some sort of analytic evaluation? I don't know what the comparison function, or does it send a bunch of values in? There is ways you could like send an email in Python. I wonder if I could like send an email through this code and have it execute. I mean, there's always those sort of concerns you have when you're sort of remote running code. That was actually a bug I found when I was a freshman in college, and we had a sort of submittee is what it was called, where you submitted your code and they would run it and see what the output is and compare it against the correct values. Well, it turns out they would let you sort of run some potentially dangerous code, and you could sort of get the output if you just emailed it to yourself and wrote a Python script to do that. So that's just a funny little aside. So we have some max here. We want to return the max. That's just a built-in function. What do I do if I get stuck? I'll never get stuck. Oh, known issues. Okay, whatever. All right. Okay, wait a minute. This is a lot of nodes. Maybe I won't do all of them. Let's see, how is this different? All about qubits. Oh, okay. So this is sort of stuff we've talked about before. I'm not going to, I guess, refer to this sort of side unless it's something I don't immediately see. This is all the basic sort of operations we've covered before. All right. So suppose we are given an unnormalized quantum state. We can turn this into equivalence by normalizing it. So what do we want to do? We want to rewrite it so that it is normalized. Well, now this is something we can do by taking the vector, well, it's just alpha and beta. Prime, I'll use proper naming conventions. And so we can think about this, right? If this is the, I guess I should use NumPy functions. I don't know if they've imported math. So the way we're going to do this for a single qubit is it's just the square root of this, the sum of these elements. So, right, if we have, and if this is equiprobable, it's just going to be 2, basically. So if we have, well, I guess this is probably too specific. They might want a general form. So we want to divide by the norm of the vector, right? So norm, for those of you who are unfamiliar, 1 pi norm. This is Bing is not what I want, because look at these search results here. My create learning Python. What even are these? If I go to Google, I can see that Stack Overflow. That's not what we want. I just want the norm function in NumPy. So we can see that this will return the norm of a given vector. So if we have this information, we can now go back and we can do this is alpha divided by alpha norm of the, yes, I have to write this as an array, alpha beta. So now we have this function here. We'll copy this over. Beta prime equals beta over. Okay. And now we can return a vector of alpha prime beta. I actually don't know what the default norm calculation is, so that might not be right. Ah, it is right. Default board, let's see, the 2 norm. Okay. Yeah, so we just want to make this the normalized vector, right? So this is going to be, in this case, right, if we did 1 and 1, so they're equiprobable. For convenience, I did not even use that. I don't know why they would want, I don't know why you would use those, but you can just divide by the norm and you'll get the proper results. All right, so now we're looking at the Dirac notation. So we have, let me just get Google ready again. So we can see that we have, write a function to compute the inner product, then use it to verify 0 and 1 is an orthonormal basis, which means orthonormal, remember that they're normalized, so everything will be less than 1 and normal, and that 0 and 1 would be orthogonal, so their inner product would be 0. So we can just do, pretty sure, I guess we'll test my NumPy knowledge here, that NumPy has an inner function that will compute the inner product between state 1 and state 2. Do not know if this is actually real. I'm pretty sure there's an outer. No. Is there no? Yeah, there's an outer. Is there no inner product? Oh, there is. Inner product of 2 arrays. without complex conjugation. Did not know that. Yeah, so that won't actually work. We're going to need to do, because they can be complex, remember. So we're going to want to do the conjugate of this state. There we go. And so that will be the that'll be the output. Actually, I kind of wonder, now that we can see, oh, I can't go back and edit it. Okay. What I want to try is actually just seeing if they actually, what sort of code. Let's just see. Yeah, I'm just trying to see if I can see how they're evaluating it. I could, obviously, it's open source. I could go look at it that way, but okay, measurement. All of this has been straightforward so far, so I'm kind of just breezing through it. Measurement is probabilistic, exactly. Right, a function takes a quantum state, complete the function to simulate the outcomes of an arbitrary number of. Okay, so we have some state, and we have our number of measurements, and this is just for a single qubit. So we have our the probability, right, of 0 and the probability of 1. So we can just get the probability vector by saying vector equals the state vector, and we want to multiply it by its conjugate transpose. No, not by its conjugate transpose. That would be the inner product. We just want to multiply it by its conjugate, right? Because this is going to do element minus multiplication. So it's going to be A times A star, B times B star, which is what we want. So then we can do numpy dot. What is the random choice? I want to say 1 B equals plot. We'll see. This is really exposing my lack of numpy knowledge. Oh, right, prop vector. Cannot cast. Oh, this probably has to be cast. State numpy dot complex. Oh, no, it's probably because it's getting. I know what the problem is. It's probably because this is a complex, right? This is a complex input, and so it still gets casts, even though this is real, right? Anything times its complex version or a complex conjugate is going to be the same. We can simply call the real on this. Does this have to be? I should check. Let's see. Oh, A has to be. If an int a range. Oh, okay. So I think this has to be. It won't include that number. It says it accepts an int. So you can see, right? This is sort of the solving method that I go through. So that's the probability. Int object is not. Oh, returns an array of ints, number of measured samples. Oh, I know why. It's because this returns a single. That's showing me. We want to return however many there are. In this case, we would like to do size. It's not just S. There we go. That took a while. It's a trivial sort of operation, but it's just my lack of NumPy knowledge. I often refer to documentation. All right, so we want to get the probability vector and then just sample from it. That's all we need to do. All right, now we need to complete the function to apply the provided gate onto the state. So we can just return, this is just simple matrix multiplication, right? So we have U times the state. I would have been very sad if that was not correct. So now we have our simulator, right? And it says we have all this stuff to write a simple quantum simulator. Remember that we've already done that before. You can refer to that video for how to write a more thorough quantum simulator. All right, so we want to initialize the state. So we have just this is for a single qubit, so it can return them by array 1, 0. Now we need to implement the quantum algorithm described above. Oh, okay, initialize state. Ooh, try to do it in 3 lines of code or less. Prepare state. Okay. So we want to do, what is that function called? Initialize state. Qubit equals initialize state. Qubit equals apply U. So now we're applying to Unitary. We're going to measure it. How many times does it say to measure it? 100 times, okay. Results equal measure state. Or they want it in 3 lines, so we can just return this. Return measure state. We have a qubit state and we have our 100. So now you can see that's correct. Yeah, so we did that. Next lesson. All right, quantum circuits. So we have our gates and wires. Pretty straightforward. Let's see if I can do this. Oh, now we're actually moving on to the PennyLane, which is probably going to take a lot more Googling because I'm not as familiar with their documentation. I only ever used PennyLane when I did the Q hack. I never used it before and I hadn't really used it since. So let's see. All right, so I just want to reorder it. So it's going to be reorder these 5 gates to match it in the picture. So we have 0, 1, okay. Then we have a Hadamard. Then we have a RX on that one. So we just need to move this one to be over here. All right. Because the C0 is the only order that was incorrect. All right, so we have devices, and I recommend for anyone a little confused by PennyLane to just check out the previous the Q hack videos. There's a series of 4 videos that should provide a thorough introduction. All right, so now, yeah, we have Q node, circuit, and device. All right. Implement the circuit by adding the gates. All right, so we have dot Rx, let's caps Rx, data, wires. Do I have to specify wires or can I just do 0? Does that work? Let's see. Oh, I have to say wires. That's kind of annoying. Why can't that just be the second argument of the function? You know there has to be wires, so anyway. So it's in this RY on the second one, and that's going to be B, wires equal 1, RZ on the third one, it's going to be omega, wires equal 2, we want C0 between 0 and 1. Wires, that's kind of annoying, 0, 1, C0, and then we have to do wires equals 1.2. QML C0, and then we have to do wires starting with the target of 2 onto control of 1, and that will yield, I believe, the absolute correct results. Let's see, submit. Oh, the wires 2, 1, oh, 2, 0, right? Remember, it goes 2 to 0, not 2 to 1. All right. Another second way to construct a Q node is to use a decorator. So instead, right over here, we explicitly called the Q node function, but we could just decorate the function using the @ that's a decorator. You'll recognize that in TensorFlow as well. TensorFlow has decorators for TF function. Q node, kind of, this is probably an easy run. So now we want to run it with the provided parameters. So we want to do my circuit theta v omega. Right, so now it just changes from calling Q node to just being able to call this function, which is kind of nice. What is the depth of this circuit above? Depth is 1. Let's see, how do they define depth? I guess you could number of gates and type of gates, however, circuit depth loosely. So in this case, right, you could consider this is, depending on how you talk about gates, I think certain types of hardware like IonQ, I think, don't take my word at this, gates can only be applied one at a time. So the number of gates is equivalent to the depth. But in this sense, it's sort of parallel, right? 1, 2, 3, 4, because that's how many things can be done in parallel. So let's submit that, and that's sort of how they're defining depth. Okay, we're already at 20 minutes. I think I'll just do the next one and then call it for today. Unitary matrices. Unitaries. This is actually an interesting thing. Everyone knows, right, that quantum circuits have to be done with unitary operations, but it's sort of like, why, right? I mean, the interesting thing that someone explained it to me, one professor of mine explained it to me, or just said it, I guess, in passing, was that, you have conservation of energy, conservation of mass, whatever, right? Unitary matrices preserve the norm of the vector that they're being multiplied by. So unitary matrices are probability preserving, which means that, right, if it was non-unitary, you could get probabilities greater than you could get like weird sort of probabilities, you could get weird information, right? I mean, if you just had like a matrix that was 1000, 0, 0, 0, that would just increase the probability by 1000, like that wouldn't make sense, right? So this is where it's that was an interesting idea. So we can use the qubit unitary to specify a unitary matrix and apply it to a qubit. So they just told us what to do. Not a lot of thinking there. Unitary. So we have our u and we have y is equal 0, I assume. Let's just look over here. Oh, just parametrization. This is the general format of U. U3 gate is what it's called in like Qiskit, I believe. Okay, next, see, this is the U3 gate, which for some reason they just call rote. Seems like U3 is a fine name, but I did not write this. All right, so we want to apply the rote and then return the state vector. I don't know what the state vector is, but handily they tell us right here. So we want to do qml.rote v theta omega and then return qml.state. All right, so far they're kind of just telling us what to do. Oh, I forgot the wires. Wires equals 0. All right, we have now finished this section, and we are on to the X and H gates. I think that will be all for today. But if this, I don't know if this is at all helpful or if it's just confusing or whatever, but maybe there will be more going through the textbook.